Welcome to the second part of Lecture 4. So in this part, we're going to focus on the multiplicities of ideals and modules and their application to equisingularity. So the multiplicity of an ideal or a module, which is M primary, is one of the most important invariants we have, and it's intimately connected with integral closures, we'll see. It has the multiplicity of an ideal and a module has both a length theoretic definition and an intersection theoretic definition. And in the applications, it has both a topological geometric interpretation and an algebraic infinitesimal interpretation. So here are some basic constructions for ideals and modules. These seem a little difficult at first, but if you work out a few examples, they are really not so bad. So we start with M, a submodule of a free module, and we can associate an algebra to it called the Riesz algebra of X. How do we do that? Well, if we take an element, M1, MP, so that's a vector because we're in a free module, then we just write it as a sum where these TIs are new indeterminates. And this is going to be the element of the Riesz algebra. Now, we can use the degree of the TIs to give a grading to the Riesz algebra. And Mn is going to be the terms of the Riesz algebra of degree n, and we're going to use that in a minute. One thing we can do is we can represent the algebra of the Riesz algebra geometrically, and I'm doing it by looking at the projective analytic spectrum. So basically what you do here, the way I like to think about it, is I just take the closure of the projective row spaces of a set of generators, of a matrix of generators of M at points, where the rank of the matrix of generators is maximal. And then we just close that up. Yep.
Two questions. One, if the rank of the free module is P is equal to 1, we get the usual Riesz algebra.
That's right, yes. That's correct.
And then the other question is, if the matrix M, what do you mean exactly by maximal rank?
Right, so the idea is I have a module, I fix a set of generators associated to those generators because they're a subset of because M is a subset of a free module, I have a matrix. And now I ask that matrix have rank, maximal rank at a point. By maximal rank, yeah, right. So by maximal rank, I mean that you look at the in general, the maximal rank will be P, but in the case that, in all cases, in the general case, the rank of the matrix is going to vary, but it's going to be maximal and it's a Zariski open set. No, the maximum may very well be less than P. Yeah. Okay, so we have this, and I think we're almost ready to, oh yeah, I want to remind people what this is in an example. So if you take the projective analytic spectrum of the Riesz algebra of the Jacobian module, then this is the conormal space of X. And it consists of these tangent hyperplanes to the smooth part, X0 means the smooth part, and the closure of the space in X cross Pn minus 1. Right, the Jacobian module has n generators because there's n variables we're working in Cn, and when we projectify, it goes to Pn minus 1. Okay, so now what is the definition of the multiplicity? Oh yeah, well here's one more piece of notation. Now we have the definition of the multiplicity, the length theoretic definition. So if I have a module such that such that it is a finite dimensional vector space, the length is just the dimension of that vector space. And You don't want to work anymore? Oops. Anyway, here's the theorem definition. So this was originally done by Buxbaum and Rim. And the idea is that you want to look at growth. You have this polynomial ring here, and we have R inside here. And then we're going to look at the length of these quotients, all the terms of degree n divided by those that are in Mn. And this turns out to be a polynomial, surprise. And the leading coefficient can be written as a number divided by d plus p minus 1 factorial. And so whatever this number is, that's the multiplicity. Well, this seems, well, let's look at an example first. So let's show that the multiplicity of the ideal, which is the square of the maximal ideal in two variables, let's show that that's multiplicity is 4. All right, so in this example, what is p? Well, p is going to be 1. And f, well, if p is just 1, then we can think of f as just being O2. No, I'm sorry, the free module is O2. And script f is O2 adjoined T1. And if we take the projective analytic spectrum of this f, it just collapses to be the spec of O2, and thus we get C2. Okay. Yep. Pardon me? It's because you think of it as an analytic space with a sheaf of rings on it. Okay, there's not much difference between the ordinary one, but yeah, okay. So we need to calculate here, according to the definition, we have to first figure out what Mn is. So we take the ideal and raise it to the nth power. So now we're going to get the maximal ideal to the 2nth power. Okay. So now we want to look at the length of this. All right. So the length of Fn mod Mn is the same thing as O2 mod M2n. And that turns out to be 2n times 2n plus 1 over 2. Does anyone see why this is true? I don't know. Maybe everybody does. All right, think about it here. We're looking at O2 t to the n times this times t to the n. So that's why this is this. And now we're looking to see which monomials are missing from M to n. And we only have two variables. So it turns out to be the sum of the first 2n integers. Well, that's what that is. So we multiply it out and we get 4 times n squared over 2 plus lower order terms, and we see the multiplicity is 4 as predicted. What does this mean? The length definition is useful for some purposes, but it's hard to use it to think about anything. So here's a little give you some idea of what these multiplicities mean here. First off, if we have d generators in a d-dimensional space, then we understand what the multiplicity is. It's just the degree of f, where f maps xd to cd. If we have more than d generators, well, we just find a sub-ideal with d generators inside I, such that they have the same integral closures. Then the multiplicity of I is the degree of f again. So this gives you a way to think about the multiplicity of ideals. But what about modules? And we call J a reduction of I. Okay, anyhow, if a module has d plus p minus 1 generators, now the multiplicity is going to count the number of times 0 is the point where the rank of m is less than p. If m has more than d plus p minus 1 generators, we again take a reduction with the correct number of generators as before. So let's do an example so you can see what I mean by this. Whoops. This is a matrix of generators for a module. And it turns out that the multiplicity is 3. I didn't prove that, but it's an exercise. And M has 2 plus 2 minus 1 equals 3 generators. So it has the right number of generators. So what I'm going to do is I'm going to deform the entries of M a little bit. And if I do that, we see there are only 3 places where M has rank 1. 0, 0, T0, and TT. Now you can see clearly that TT is one of them because that kills off the first row. And 0, 0 is another because that kills off the second row. And T0 kills off 2 elements here. Let's see. Whoops, is this right? Oh yeah, yeah. T0 kills off this guy here and this guy here. And so you're just left with a single thing here. All right. So for M, we should count 0, 0 3 times when counting the number of points where the rank is less than 2, and the multiplicity of M does this. Where do we get this magic number from? Well, if you think about a P by D plus P minus 1 matrix, the expected codimension of the set of points where the matrix has less than maximal rank is D. Let's just remind you of the shape of the thing. So think about this as being the identity block, P minus 1 by P minus 1. That means we have D slots left, which have to be 0 to define something of which has less than maximal rank. D being the dimension of X, this gives us something of dimension 0, and that would be the expected dimension. So there's a nice thing about using the expected dimension, which means that when you move, you don't lose any points, which is good. Okay, so now we want to talk about reductions of modules. We mentioned what they were here. Our goal that we have in mind is that we want to be able to show that this guy, who was the actor we left last time, contains the partial derivatives of f with respect to y in its integral closure. That's the result, the hypothesis we need to use the theorem that we proved in part 1. So again, given f and fp are a submodule, then R is called a reduction if they have the same integral closures. Oh. Okay. Now, here's where things become interesting. If we have H as a section of N, then H and M generate ideals on progen of Rn. Let's denote them by rho H and script M. How does that work? This is my element H. That's H. Ni is a set of generators of N. Now, if I look at the projective analytic spectrum in the chart in which T1 is not equal to 0, we have rho of H is equal to summation of GI Ti divided by T1. So this gives me an element of a sheaf of ideals. So here's a geometric interpretation. I have the Jacobian module. Your question?
Yes, the first sum, Pi and I, it goes over all the generators of n. The second sum, does it omit I equal 1?
No. I equals 1 is part of the thing too. Or actually, it would be G1, right?
Okay, so one of the terms is G1 times 1.
Right. Yep. Okay, so if M is the Jacobian module of X and N is a free module, then what is the vanishing of this ideal? Let's try to get used to it. Well, it's going to consist of points, pairs, X and L, where X is an X. Now, L has to be in the thing we get when we look at the progen of Rn. Well, if N is a free module, then we're just looking at the projectivization of the Hom space. Or you can just think of it as hyperplanes, either one. And then what we're saying is that when you take L and apply it to df of X, you should get 0. So if H is the hyperplane, which is the kernel of L, then the image of df of X lies in H. Okay, so the vanishing of M is all those hyperplanes which contain the image of df if we're working with the Jacobian module. Now, one of the nice things about doing this, it allows us to strip out one copy of N from M, as the following example shows. So here I have the Whitney umbrella and the singular set of the Whitney umbrella. That's really what I want. Let's see here. Yeah, so this is the Jacobian ideal of the Whitney umbrella. Now the reduced, no, this is not equal to J. Okay, so maybe I called it, oh, I see. So I called, N is going to be this ideal J, which is going to be XZ. So I is the Jacobian ideal and J is the ideal that defines Y. Okay. Now, what we're interested in doing is we want to look at what we get for M on this Riesz algebra. So the Riesz algebra looks like O3 because we're in 3 space. And we have our 2 generators, XS and ZS. And this is going to be isomorphic to this ring here by this map here. And we recognize that as the blowup of C3 by J. All right, since x squared is equal to x times x, and xy is y times x, and z is z, the map from the Riesz algebra of I to R as image xt1, yt1, and t2. So we've seen that we have stripped out from these coefficients one copy of the ideal of n, or j in this case. Okay, so now we check, and we look at the ideal sheaf this induces on proj n. We see there's only one point where all 3 of these guys disappear. If T2 is 0, then we have to be at the point 1, 0. And then if T2 is 0, T1 is 1, and so x and y are both 0. So we get the origin cross 1, 0 as the only point in the vanishing of M.
What about the z-axis, where the things are similar? There's one more earlier, right?
Let's see here. Oh, maybe, well, let's see here. No, maybe you're right. Maybe you're right. No, I'm sorry, you're right. It is supported not just at that point 0, 1, 0, but it's actually on the whole z-axis. Very good. That makes sense because the z-axis is a singular locus, after all. Supposing I take my submodule M and I write it as N applied to this matrix F, then if we let F be the ideal sheaf induced on proj Rn by this module F with matrix of generators F, then actually this is in disguise, this ideal sheaf is just tilde, is just script M again. And then the theorem is that M bar is equal to N bar if and only if the vanishing of this is empty. Now this is the first of a couple of propositions that I don't have a chance to prove, but the proof is in the notes. And a problem that's kind of easy to do is to actually go in there with your bare hands and show that this ideal, which we know is a reduction of this ideal, and to show that V of F is empty. Now, if we have the situation we had before, M contained in N, then we have an inclusion from M into N, and that gives us a map from proggen Rn minus V of F to proggen Rm, which is just, which you can think of just as projection. Here, I've written it out. We take a point xp in here. So it's a point x, and this p is some kind of line. And we just map it to x of fp, where fp is a valuation of p of the set of generators of f, which come from the columns of f. And that gives us a map. And the corollary is that if m and m is above, then m is a reduction, if and only if V of f is empty, if and only if the induced map pi m is a finite map. All right. The point of doing this was I wanted to bring, we're heading towards the point where we can show that actually any module, which is a submodule of a free module of finite co-length, has a reduction with only d plus k minus 1 elements. So we're going to creep up on it a little bit. So suppose the fiber of proggen Rn over x has dimension k. Okay, then n has a reduction m, where m is generated by k plus 1 elements. How do we connect this fiber dimension with these k plus 1 elements? Well, we think of this projective space as being contained in x cross pg minus 1. G here, G is the number of generators. G is the number of generators of n. So we choose a plane in here of codimension k plus 1, so the intersection of our plane and the fiber of proggen over x is empty. We can do that because this has codimension k plus 1, and the fiber dimension here is k. Well, we choose coordinates on pg minus 1 so that our plane is given by the vanishing of the coordinates t1 through tk plus 1. And then choosing these coordinates is equivalent to choosing generators on n. So let m be the submodule of n generated by the first k plus 1 generators of n if the new choice of generators. Then the projection onto these first k plus 1 coordinates gives a finite map, and so m is a reduction of n. Okay. And then we can say that we finally get to the point we wanted to get to, that if we had n and f, xd equidimensional, n has generic rank E on each component, then n does have a reduction with d plus e minus 1 generators. Okay, so where does the d plus e minus 1 come from? Let's see. All right, let's do counting here. The generic rank of n is E. That's given to us. The generic fiber dimension of proggen Rn then is E minus 1 because we subtract 1 when we projectivize. So the dimension of the whole thing is d plus e minus 1. Okay, so what's the largest that the fiber over 0 can be? Well, the answer is d plus e minus 2. And so we use the previous one to get d plus e minus 1 generators. And that's what we're saying here. The largest the dimension of the fiber over x can be is d plus e minus 2, and so n has reduction with d plus e minus 2 plus 1 generators. So here's a little exercise. Show that H is not a limiting tangent hyperplane of X if and only if the submodule of JMX generated by the partials with respect to elements of V is a reduction. And the hint is to show that V of F is empty. So here comes the multiplicities. If you have a reduction, then it's always true that they have the same multiplicities. And if they have the same multiplicities and the space is equidimensional, then they have the same integral closures. Okay, if we have a Cohen-Macaulay ring, we can do better. If M has the magic number of generators, D plus P minus 1, then the multiplicity of M is known. It's just the co-length of M. And it also turns out to be the co-length of Jm, the ideal of maximal minors. So we have a little example which I'd like to do. Supposing I have an isis, which is a curve, and it's going to be defined by homogeneous forms of degree di. Let's calculate the multiplicity of the Jacobian module. Okay. Let's see how we get this number here. Well, the first thing is, what is X? Well, X is homogeneous, and our equations have degree di. That means that if I think of these as defining a set of points in Pn minus 1, the number of points I get by Bezout's theorem is just the product of the di's. Now, choose n minus 1 columns of the matrix of partial derivatives, such that the submatrix n has rank n minus 1 on X, that's the maximal rank, except at 0. And we denote the module they generate by n. We can assume n is a reduction of Jm of X, but by choosing it well. Okay, the determinant of n is homogeneous of degree, well, what is it? Well, we have n minus 1 rows. That's that sum there. And these are the degrees of the rows, di minus 1, because I took partial derivative. And by the theorem of Buchsbaum and Rim, the multiplicity of n on each line is just the co-length of delta n in oh dear. It's just the co-length of the determinant in OX by the Buchsbaum-Rim theorem. So that means that I have we get the sum of the degrees on each component, and so this is the degree on each component, and these are the number of components, and so the total is the multiplicity. So this is an example where it's not too hard to actually calculate what the multiplicity of a module is. Now I'd like to show the connection between the multiplicity of a module and the Legge-Royal theorem. So this is a little bit different than the theorem that Juan talked about last time. If I use H, which is a hyperplane, which is not a limit tangent hyperplane at the origin, the multiplicity of JMX is just the sum of the Miller numbers here, μx and μx intersect H. So let's see how we prove that. So this is the original Legge-Royal formula here. X is defined by F. F is a map with components Fk. X prime and isis defined by a map with one more component. And I is the ideal generated by these guys. And the minors in the larger one. Okay. So we're going to now prove the theorem that we had it on the board before. So L is going to be a linear form defining H. We're going to let L be the extra function, the new function in the formula. So the right-hand side of the formula becomes the Miller number of X plus the Miller number of X intersect H. And then the multiplicity, because here I'm using the fact that this is a reduction. This is a reduction, so this is equal to whoops. Yeah. So here I'm using the fact that that E of Jm of X of H, which is the partials with respect to the vectors in H, is a reduction, so it has the same multiplicity as Jm of X. Now, the ideal of K plus 1 by K plus 1 minors of a matrix of generators of this Jacobian module is the same as the idea of K by K minors of the generators of this guy here. So this implies that the colength of I by the Buchsbaum-Rim formula is the multiplicity of Jm of X H, which is the same as the multiplicity of Jm of X. We want to calculate Miller numbers inductively. First proposition. Suppose I defines an isis of dimension 0. Then the Miller number of X is equal to the multiplicity of the ideal minus 1. Why is that? Well, if I is an isis, then I is equal to its generator has n generators. And then we know that the multiplicity of I is the degree as a map from Cn to Cn. The number of points is the multiplicity of I, not a critical value. So if we fix a common point, so we have a common point for every zero sphere, we had p points altogether, but we're going to get one less because we've fixed one of our points, and then we get ei minus 1 zero sphere. So the Miller number is the multiplicity of I minus 1. Oops. There we go. Anyway, we now can calculate the Miller number of a family of n lines, as long as they are in isis. So let's just see how the computation goes. We know that the multiplicity of the Jacobian module is mu of x plus mu of x minus h. So solving for mu of x, we have to subtract off mu of x minus h. And then we know what this is. And we know the multiplicity is just the number of lines minus 1. And then we just do the math, and the result follows. So now I come to the big gun in the subject as far as equisingularity goes, and that's the principle of specialization of integral dependence. First proved by Tessier in '73 for ideals, and our proof, which I did with Stephen Kleiman, and which appeared around '96 or so, uses ideas which appear in Tessier's paper in 1980. Okay, so here's the theorem. We assume that x is equidimensional and that y, the function that goes from y to the multiplicity, is constant on y. We start with a section of a free module whose image is integrally dependent on m of y for all y in a dense Zariski open set. Then h is integrally dependent on m. I want to give you an example which shows how this is used. It'll also help you to see what the theorem means. So I want to start with the function f equals x to the n plus y to the n plus th. So this is a family of functions. H, we assume, is in the maximal ideal raised to the n plus first power. Now we're going to work here. We're not going to work on the zeroth set of F. We're just going to work on O2. And what we want to look at is the integral closure of M2 times the Jacobian ideal of Fy. I think I wrote it like this morning. Ft, actually. And we'd like to figure out its integral closure. Well, here's the argument. If you think about M2 times the Jacobian module of F0, that's just M2 times x to the n minus 1, y to the n minus 1. And this contains xn, yn. Does anybody remember what the integral closure of this was from this morning? The integral closure of this was... Yeah, so it's all the monomials of degree n or more. Now, the argument that we used to prove this, you have to check it, but it also shows that this is actually equal to it's mostly because, intuitively, it's because this h is in n plus 1. So when we look at curves, it can't interfere with anything. Okay, so we know that E of JF0 equals E of JFT for all t. All right, that was one of the things we had to check to make sure the theorem worked. We needed to make sure the multiplicity was constant. And then the other thing we had to check was that the partial of f with respect to t restricted to t equals some value, t naught, that is contained in mn JFT. And and this is true, we checked this too. This checks because this is equal to h. This is equal to h, and h is contained in m2n plus 1. So the conclusion is, the conclusion is that the partial of f with respect to t is contained in m, what I called y this morning, JF. And this will in fact imply that f inverse of 0 is, well, of course, it's just going to be a line in this case. Whitney equisingular. is W. It's not much of a set because it only turns out to be the y-axis. That's all we get. Or the t-axis, rather, sorry. Okay. But this is, you can see how this makes things much easier. All we have to do is calculate these multiplicities. And in fact, this condition is, in general, known already from stratification theory. So all you really have to do is check the multiplicities when you apply it to to stratification problems. Well, we don't have time today, unfortunately, to talk about the proof, I don't think. So we have to skip this bit here. Instead, I want to go to talk about maybe this last one's right. Okay, I'm sorry. We do want to do this part here. There we go. Okay, so this is the sufficiency part. So again, we go back to a family of lysis over yk, and we ask that the multiplicity of this module is independent of y. Then x minus y is smooth, and the pair x minus yy satisfies W. In particular, all the members of the family are topologically equivalent. Well, it turns out that we didn't prove this, but it's true that the multiplicity of y is upper semi-continuous. Now, let's draw a picture here. So here we have this point here. Here we have x. This is y. All along here, multiplicity of my, j, m of f, of x, right, actually, is constant. What would happen if we had something like this? So these are going to be other points. So these are points where say Jm of xy is less than p. If this was true, then the multiplicity here would be this, which is the same as this, plus something else. So we would see that the multiplicity would jump. The multiplicity would increase, and that's not allowed. So this curve here can't exist. Now, if that curve doesn't exist, then that says that my set is smooth, except along the y-axis. Okay. Because W is generic, we already know that the partial respect to YL is contained in the maximal ideal, in this integral closure anyway, for a Zariski open set. W only fails on a Zariski closed set. So now we apply the PSID and we have it hold at all points, and the family is W equisingular. So we have an expansion formula that relates the multiplicity of M times the Jacobian module to the mu star invariance. Those are well, let's see. I don't know if we've done those yet, but the mu star invariance, these mu's here, these are the Milnor numbers of various sections we can take of X. And it turns out that we get the multiplicity of X plus the multiplicity of the Jacobian modules of these guys here. And this brings in these mu star invariants. And that was in Yaffe 96. And then here's a corollary. Supposing these are independent of Y. Whoops. Oh dear. Yep. Yeah. So suppose these are independent of Y. Now here we have a sum, right? These are independent of Y, but all of these invariants are upper semi-continuous. If these are upper semi-continuous, then their sum must be constant, if they add up to something constant. So that implies that these are all independent of Y as well. So here's the proof of necessity. Yeah. The mu star sequence of XY is independent of, I'm sorry. So supposing we satisfy W, if W holds, then all of the elements here are homeomorphic. And so we know that And actually, it's stronger than that. Tessier proved that if W holds here, then not only are all of the members of this family homeomorphic, but all of the members of the associated sections are homeomorphic too. So the mu star sequence of xy is independent of y, and hence so is the multiplicity of the maximal ideal times the Jacobian module. And that gives us a necessary and sufficient conditions for the Whitney equisingularity, or for the W equisingularity of families of isos, and that finishes the talk. Thank you. Any questions? Yeah.
Maybe to extend this specialization principle, you have integral dependence, you could... Okay, to understand this specialization principle a little more geometric, you could try to write down integral dependence over geometrically closed points, point by point.
Right.
Usually,
that's right.
You would not finish because it's infinitely many.
Right.
So then you find some Zariski open subset where integral dependence holds.
Right.
And say this Zariski open subset has parameters y.
Yep.
Then you really get an integral dependence over, not over a field of coefficients, but over a ring with these variables y.
Yes,
inside,
that's right.
Right?
Yep.
And then the statement is what? That
the statement is, for it to extend, you need the multiplicity as constant at each point in y. We need the multiplicity of the module is independent of y as you move along the parameter space.
In this open set.
No, period. That's how you close. You move to the closure because the multiplicity at the points in the closure of the open set have the same multiplicity as the points in the open set. It's always true that you can find a Zariski open set where the multiplicity will be constant along each of the points. So you need to know what's happening at the boundary. And the great thing about this result is all you really need to know is the algebra. Is the algebra still independent of parameter? If it is, hey, you're done.
Okay, thanks.
But that was a nice way to phrase the whole thing.
Let's go back to the examples. If I understood well, if you have a Newton diagram, then every deformation for hypersurfaces above the Newton diagram is trivial. Does that follow your theory?
Yeah, so what we know, for example, is that if the function is Newton non-degenerate,
yes,
then if we deform it by terms above or on the diagonal, at least for sufficiently small t, it'll remain Newton non-degenerate. And so the Newton diagram for each of the functions in that family will be the same. It won't change.
Yes. This includes also deformations on the Newton diagram? Question mark.
Yes, but for on the diagram, you can only go a little bit. If you're above the diagram, you can go on forever.
Okay. Thanks.
Yep.
Any more questions? Okay, let's thank the speaker again.
Thank you. Thank you. I'll take one of these.
Can I start? Okay. So I promised I'll work out this example. As I said earlier, you can calculate the monodromy of this polynomial at the origin and show that the eigenvalue 1 doesn't appear. And hopefully you'll see that in the next section, in the next exercise section. What I want to do now is to actually try to employ a little bit this formula for the Euler characteristic and showing that something is a rational homology manifold, because this is typically more difficult. So let's see, how do you show that something is a rational homology manifold? How do you show if something is a manifold? Well, you should show that at every point, if you take a little neighborhood in the ambient space and you intersect it with your variety, the intersection is a topological sphere. In this case, we want to show the intersection is a space which has the same homology over the rationals as a sphere of the appropriate dimension. Now, this means that we actually will have to look point by point at links, what's called links of such points in the variety. Of course, it makes more sense to try to break your space into equisingular pieces and try to do this story at each point, at one point for each such piece. Because the topological type is going to be constant along each of these pieces you break your space into, the so-called Whitney stratification. So in our case, if you actually write down the singular locus, let me just call it sigma. So you take the partial derivatives of this polynomial, vanish them, and see what you get. You'll get a projective line of coordinates. Okay, so here I use the coordinates x1, x2, x0. Let me switch to my notation. I'm just gonna call them x, y, z, t, and v. So this should be x squared z plus x cubed plus tx squared plus v cubed. So the coordinates in my case are x, y, z, t, v. So these are the coordinates of CP4. As opposed to x0 up to x4. Okay, so if we actually do the calculation, what we get here is the line, the projective line, corresponding to the vanishing of x, y, and v. So we call this standard in algebraic geometry. I guess v is taken already. Is z maybe allowed? The zero set of x, y, and v. Okay, so it is a one-dimensional projective line. I drew this picture here of the Whitney umbrella because up to adding this last cube in the new variable, in the last variable, this looks almost like the Whitney umbrella. So now, like in the case of the Whitney umbrella, one point on the singular locus looks different from the rest. And that point is going to be zero, 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 1, 0. So this is different from, let's say, 0, 0, lambda 1, 0 with lambda not 0. So why is it different? Well, it's exactly the story like here. You look at the tangent plane or tangent space at the point on the singular locus. In this case, you have two lines all the way to the origin, in which case you get a double line. So the story replicates here. You'll have two planes. For lambda not 0 is the tangent space at such a point, and the double plane at this point. So I guess it's easier to do this in the affine picture, in the affine coordinates. So bear with me for a little bit till I work out the stratification. So let H be, let's say t is equal to 0. In my notation earlier, this is z of t. This is the hyperplane at infinity. And now, here, if I take out now, let's say I look in the affine patch away from this hyperplane, so v minus h, what I get is the surface given by the threefold given by y squared z plus x cubed plus v3 equal to 0 in C4. Now again, up to the last cube, this looks almost like the Whitney umbrella, except that the Whitney umbrella has a square here as opposed to a cube. So this picture is by no means the picture of this story, but it's something similar, and I didn't want to try. Actually, I wish I did this. I didn't actually I should have drawn a picture of this to see how it looks like. Okay. So now here, the singular locus of x, well, it's just like before, right? So I have 0, 0, z, 0. So I'm eliminating t from the picture. Or if you like, if I want to put t back, this would correspond to a 1 here with z and c. And I like to write this coordinate by simply forgetting t here. Okay, so now on this complex line, it's easier to actually work out the tangent space, and you get exactly what I said. So at let's see, maybe that's right, tangent cone at 0, 0, lambda 0 is two planes if lambda is not 0, and double plane if lambda is 0. So now this says that the origin on the singular locus will have to be a separate stratum. Yes, go ahead.
This is a stupid question. In the formula for x, isn't there an x squared missing? X cubed plus t equals 1?
Oh, x squared.
X
You're right.
squared,
You're
right?
right. Sorry. Where is it? Yeah. Oh, yeah. So then this is the Whitney umbrella.
No, both. X cubed should be there and
Yeah,
x
but
plus, okay.
up to a change of coordinate, this is like x squared, right?
Okay.
So this is like the Whitney umbrella then. I mean, except v cubed. So, okay. Yeah, there was a reason then I didn't draw this, because I must have seen it as a Whitney umbrella. But you're right. Yes, I screwed up here in my notes. All right, so now, if you know anything about stratifications, even if you don't know anything about stratifications, and if you want to do it on the nose, you say, well, I take the singular locus as a first guess of a stratum, and then I look in the singular locus for points that look alike. Whenever something jumps out of the topology of most points that look alike, the jumps should be pushed down in lower dimensional strata. In this case, there is not much except this special point. So a stratification here, in fact, a Whitney stratification, has strata given by, well, so one-dimensional stratum, which I call S1, which is the singular locus minus the special point, 0, 0, 0, 1, 0, and then the special point is the stratum in itself, a zero-dimensional stratum. And of course, the rest, right? So there is an S3, whatever it is, which is V minus S1, minus sigma. But this doesn't play much of a role in the calculations. All right. So again, I use the analogy to the Whitney umbrella for the stratification. And of course, if you know computer algebra and things like this, you should perhaps be able to guess what the Whitney stratification is, and then by various methods to check if it is a Whitney stratification or not. All right, so this is a stratification I'm going to work with. And now let's move back to our goals. So I want to calculate the Betty numbers of this hypersurface. Keep in mind these goals here, whatever I wrote, but I will eventually now go back to, can I click Z and get back the picture? Yeah. All right, so now Lefschetz tells us that Betty numbers below the middle are those of the ambient projective space. So this is a threefold, so B0 of V, so V is F is equal to 0, right? I should put it somewhere. So B0 is 1, B1 is 0, and B2 is 1. Now, V is irreducible, and we saw today that the number of irreducible components gives us the top Betty number. So B6, so this is a threefold, complex threefold, has real dimension 6, and B6 is 1. So now we want B3, B4, and B5. Now, if you try to apply Kato, so Kato said, if S is a dimension of the singular locus, N is 3 in our case, S is 1, then our V has the same Betty numbers as the projective space in the range from N plus S plus 2 to N. But in our case, N plus S plus 2 is 6 as N. So Kato doesn't tell us anything new except what we already knew, that B6 is 1. So Kato, nothing new. All right, so now what I want to move on with is to try to see why this guy is a rational homology manifold. So I'm going to do the following. I'm going to look at the Milnor monodromies transversal to strata. So maybe I should write somewhere, and let me write it here. So V is a Q homology manifold if and only if the transversal monodromies to strata, or transverse, well, how to call them, monodromies of transversal Milnor fibrations, transversal to strata, do not have eigenvalue 1. So do not have 1 as eigenvalue. So this is a consequence of long exact sequences for Milnor fibrations, just like you do to get the exotic spheres, for example, like in Milnor's book. And I think this formulation appeared first in a survey paper by Alan Durfee, or maybe Dirk also has it, so it's something known. So all I have to do now is to actually look in the transversal direction to strata, figure out what my singularities look like there, calculate those. So let's make sure. So along the singular locus, except this bad point, I'm going to take a 3-plane transversal to this P1 at some point, and I'm going to see how the singularity looks like here in this direction. I don't know how, I'm not very good at drawing this. I don't know, something there. Calculate this Milnor monodromy after you know the local equation of the singularity here. And C doesn't have the eigenvalue 1. Now, the transversal singularity for a zero-dimensional stratum is the usual singularity. So you have to work in the Milnor ball and Milnor tube and so on, and take a local smoothing and all of that. So we have, fortunately, only 2 strata, the origin and this one-dimensional stratum, and we can do the calculation by hand. And let's see what we get. Okay, now I cannot move this one. I need this one. Okay, I'm not too tall to write there, so I have to move this one. Okay. Oh. All right. First, transversal singularity to the stratum S1. Let me write it like this, and I'll explain it in a minute. So how do I do this? Well, maybe I should say how I do this. So I take a hyperplane. So the singular locus is one-dimensional. The transversal direction means I have to consider a hyperplane intersecting with the singular locus and see how the singularity looks like. All right, so choose our VFT. So this was the thing at infinity. So it has coordinates x, y, z, 0, v. So this is a CP3. This is transversal to our sigma, which was v of, not v, sorry, z. The 0 set of x, y, v at their intersection point. Which is 0, 0, 1, 0. So now I have coordinates x, y, z, v in CP, sorry, in z of t. So this was our one-dimensional singular locus. I intersect with the hyperplane, and they are transverse. But so I choose it transverse at this intersection point. I have to work in a normal direction to the stratum, right? All right, so this is now I can work in this slice, z of t. And the singularity there looks like, so singularity at this intersection point, which I'll just write 0, 0, 0 in C3 with coordinates x, y, v is defined by y squared plus x cubed plus v cubed is equal to 0. So there are a bunch of reductions. Did I miss something? X squared. I think it's x cubed, no? Oh, sorry, I missed that again. Okay. Right. All right, so oh yeah, sorry, good point. I killed t, right? So t is 0. T is 0. This should not be here. Good point. That was Alex. I heard that. So I work in the slice t is equal to 0. So I don't have that x squared piece. I work in this slice now, not out of it. So this slice is t is equal to 0. Yeah, sorry, I made this calculation by hand, so there is some possibility that some things are not right, but if we're all paying attention. In any case, this is a, doesn't matter if it's this or the other singularity, they're the same. This is, yeah, it's a Briskern type singularity. So for these things, we know everything, right? So what do we need? So we need, for example, the transversal Milnor number. So this is for the Parosinsky-Pragash formula. So that's what? So let me write it like that. 1 coming from the one-dimensional stratum and transversal coming from a transversal Milnor fiber. So whenever you have a Briskern type singularity, all you have to do is to take products of exponents minus 1. So 2 minus 1 times 3 minus 1 times 3 minus 1, that's a 4. What is the Milnor fiber in this case? You take topological joints of Milnor fibers of the summand. So this is a polynomial written as sums of polynomials in different sets of variables, each of which has its own Milnor fiber, and the sum is going to have a Milnor fiber, which is a join of the individual Milnor fibers. So here, for y squared, the Milnor fiber is 2 points. Y squared is equal to 1. Then for x cubed, I have x cubed is equal to 1. That's 3 points. And then similarly 3 points. Well, this is an isolated singularity at the origin in C3. So the Milnor fiber should be a bouquet of 2 spheres. And how many? There are 4. So it's not too hard. We already know what this is. But I wanted you to see it like this too, right? So if you take the 2 points, join 3 points, this is like the suspension of the 3 points, sorry. So this is, it's an S1 wedge S1. And then if I take another suspension with 3 points, well, you have to take all the lines between this picture and those 3 points, and you get a bouquet of 4 spheres, 2 spheres. So this is, again, something that, for example, if you look in my book, I have a whole section dedicated to Milnor fibers and Briskern type singularities and things like this, how to do calculations. And this would be perhaps a good, useful resource. But of course, Milnor's book, original Milnor's book or Dimka's book have as much, if not more, in there. All right, so we're done with the transversal singularity at the point S1, and now let's deal with what happens, sorry, the stratum S1, let's see what happens at stratum S0. So allow me to erase something. I'll erase this. Oh yeah, I should have said something about the Milnor the actual Milnor monodromy, because I need that. So the Milnor, the characteristic polynomial, Okay, so the eigenvalues of the monodromy are obtained from taking products of the eigenvalues of individual monodromies of summons except one. So for y squared, the only root of unity of order 2 that's allowed is -1. For x cubed, you take a root of order 3 and the square, and similarly here. Then take products of all of those. And the characteristic polynomial of the monodromy is going to look like so I have the eigenvalue -1 twice. So -1 comes from -1 times xc times xc squared, and then -1 times xc squared times xc. Okay, xc times xc squared is the cube, which is 1. And then there is also whatever is left is t squared minus t plus 1. Again, it's something of degree 4, which is exactly the corresponding Milnor number. The degree of the characteristic polynomial of the monodromy is the Milnor number. But you see, there is no eigenvalue 1. So this is exactly what we wanted. So no eigenvalue 1. Okay, now, I need to rush a bit. For this one, how does how does the hypersurface look like at this point? Well, t is equal to 1. So at S0, V looks like y squared z plus x cubed plus x squared plus v cubed at origin in C4 of coordinates. I'm sorry, I'm being so sloppy here. I just want to write the coordinates x, y, z, v. So t was 1. Okay. So now I have to calculate the Milnor monodromy for this guy and do the same what we did earlier. And now, okay, so what is the Milnor fiber? Maybe let me write this. So this is the same as, I keep saying this, but I never write it down. So by some analytic change of coordinates, you can make this precise. This is the same as this 3/4 suspension of the Whitney umbrella. And now here I can calculate everything. So the Milnor fiber, how is it computed? Well, again, I have summons in different sets of variables. I can calculate Milnor monodromy or Milnor fibers independently and take their join. So you saw this in Dirk's exercises or I don't know which session was it, but he did it. So this is just this one. So y squared z is equal to 1. That's the Milnor fiber. Z is not 1 and y is whatever. So we have an S1 coming from here. Then from x squared we have 2 points. And then from v cubed we have 3 points. So now the S1 join 2 points. The suspension of S1 is a 2-sphere. Join 3 points. What you get is an S3 wedge S3. So this kind of things you should try to visualize on your own and try to convince yourself that these are indeed the answers. So the Milnor fiber at the origin of this polynomial, or this polynomial, is S3 wedge S3. So this says, well, for example, we need a Euler characteristic of this guy. The Milnor fiber of the origin is what? I have something in degree 1, sorry, in degree 0, which is 1. And then I have something in degree 3, which is 2. So 1 minus 2 is minus 1. 2 cycles in degree 3. As for the characteristic polynomial of the monodromy, let me write it here. The same story applies. You understand the monodromies for the pieces, and then just take products of eigenvalues except from 1. So let me write this down, because I think I'm running out of time. So let me write this down. So you get t squared minus t plus 1. I think. At least this is what. Anyways, there is no eigenvalue 1. So no root 1 here. So no eigenvalue 1. So altogether, we show that the two transversal Milnor monodromies do not have eigenvalue 1s. This tells me that this V that I started with is a rational homology manifold. And now I can actually put things together. And it takes me 3 minutes, and I'm done. Okay, so V is key homology manifold. So then by Poincaré duality, we have that B4 of V is the same as B2, which was 1. B5 is the same as B1, which is 0. And the only thing that's left is B3. And B3 is 4 minus the Euler characteristic of V. Now, Parusinski-Pragas tells us how to compute the Euler characteristic. I'll write it in this setup. So let W be a smooth threefold. So degree hypersurface in CP4 of degree 3. So then Parusinski-Pragas formula says, okay, I should still have that, says the Euler characteristic of our hypersurface compares to the Euler characteristic of this smoothing by simply dropping the contributions coming from the singular strata times the transversal Milnor information away from the base locus. That was the formula. So I'm going to write here. So this was the first stratum, one-dimensional stratum minus the base locus, meaning minus W, times, remember that in the transversal direction, I had to look at the Euler characteristic of reduced cohomology of the transversal Milnor fiber. But in this case, the only thing that's left is this guy, M1, mu1 transverse. And then I have a contribution from the zero-dimensional stratum. Well, that's a point, doesn't contribute much. And then I should take the characteristic, the Euler characteristic of the reduced cohomology of the corresponding Milnor fiber, and that was that one, F0 minus 1. So W is a smooth hypersurface at degree 3 in P4. I have to throw out its intersection with S1, which was a projective line. So they intersect in 3 points. So this is, well, I'm throwing out 3 points. This was 4. This is 1. This was minus 1. And in the smooth case, I calculated this. I don't know the answer now, but you should get the answer 4 here. So the Euler characteristic is computable like this, and this will tell us B3 is 0, which is yet another way, well, complicated way of showing that this hypersurface is the same Betti numbers as CP3. I wanted to actually do this because it shows you one instance of showing that something is a rational homology manifold. It shows you a Whitney stratification and more Milnor monodromy calculations. Let me conclude by saying that everything I talk about here and summer previous summer lecture notes and videos and everything are already posted on my webpage. So if you Google my name and go under publications, on the bottom there is CIMPA lecture notes and all of that. There is a folder. I'm going to send the link once again to the organizers here, and they'll post it, but you don't need to register for the conference or anything to access this material. Okay, I'm done. Thank you. So I'll conclude by saying that I'll be here next week too. So if you actually have questions or you want to chat with me about anything, this stuff or other stuff, feel free to approach me. I don't bite.
Any question, comment? Got the microphone?
I want to announce that in the exercise session, I will repeat part of this kind of monodromy computations and show some examples, concrete examples of the things I talked about in the earlier time. But I propose that we meet already at 4:30. Then I show you also some pictures with server.
So, comment, question? Okay, let's thanks again.
Elas fecham o verão. É pau, é pedra, é o fim do caminho. É um resto de toco, é um pouco sozinho. É um caco de vidro, é a vida, é o sol. É a noite, é a morte, é o laço, é o anzol. É peroba do campo, nó da madeira. Cainga, candeia, é uma tita pereira, é madeira de vento, tombo da ribanceira, é o mistério profundo, é o queira ou não queira, é o vento ventando, é o fim da ladeira, é a viga, é o vão, festa da comieira, é a chuva chovendo, é conversa ribeira das águas de março, é o fim da canseira, é o pé, é o chão, é a marcha estradeira, passarinho na mão, pedra de atiradeira, uma ave no céu, uma ave no chão, é um regato, é uma fonte, é um pedaço de pão, é o fundo do poço, é o fim do caminho, no rosto desgosto, é um pouco sozinho. É um estrepe, é um prego, é uma ponta, é um ponto, é um pingo pingando, é uma conta, é um ponto, é um peixe, é um gesto, é uma prata brilhando, é a luz da manhã, é o tijolo chegando, é a lenha, é o dia, é o fim da picada, é a garrafa de cana, o estilhaço na estrada, é o projeto da casa, é o corpo na cama, é o carro guiçado, é a lama, é um passo, é uma ponte, é um sapo, é uma rã, é um resto de mato na luz da manhã, são as águas de março fechando o verão, é a promessa de vida no teu coração, é pau, é pedra, é o fim do caminho, é um resto de toco, é um pouco sozinho, é uma cobra, é um pau, é João, é José, é um espinho na mão, é um corte no pé, são as águas de março fechando o verão, é a promessa de vida no teu coração, é pau, é pedra, é o fim do caminho, é um resto de tudo, é um pouco sozinho, é um passo, é uma ponte, é um sapo, é uma rã, é um belo horizonte, é uma febre terça, são as águas de março fechando o verão, a promessa de vida no teu coração, é pau, é pedra é o fim do caminho, é um resto de tudo, é um pouco sozinho, é pau, é pedra, é o fim do caminho, é um resto de tudo, é um pouco sozinho, pau, pedra, fim do caminho, resto de tudo, um pouco sozinho, pau, pedra, fim do caminho, resto de tudo, um pouco sozinho, pedra, caminho, pouco sozinho, pedra, caminho, sozinho, pedra, caminho, eu tô. Não quero lhe falar, meu grande amor, de coisas que aprendi nos discos. Quero lhe contar como eu vivi e tudo que aconteceu comigo. Viver é melhor que sonhar, e eu sei que o amor é uma coisa boa, mas também sei que qualquer canto é menor do que a vida de qualquer pessoa. Por isso, cuidado, meu bem, há perigo na esquina. Eles venceram e o sinal está fechado para nós que somos jovens. Para abraçar seu irmão e beijar sua menina na rua. É que se fez o seu braço, o seu lábio e a sua voz. Você me pergunta pela minha paixão. Ainda somos os mesmos. Ainda somos.
Riemann-Steiner surface, and I know the equation by head, x there square y up squared plus y up squared z squared plus x up squared star x y z up squared is 0. Okay, the first we take this equation, and it's all over the reals, so it's clear that you see nothing. So since only the origin is satisfied over the reals, this, to show that there is a picture, you can put some extra a in it. Okay, that we're going to do. Now I can choose other languages. And what happens if we choose this extra a? Just let's make this smaller and smaller. So here it was a was 0, so we had nothing. And now you see that, in fact, the 3 coordinate axes, they are part of this non-isolated singularity. Of course, this is already smoothing of it, but it is a smoothing which is quite near to it. And I can even make this bigger, and then you can see that this is smoothing. Now I'm going to make the Riemann-Steiner surface, and I will do this by adding b star x star y star z. Okay, now there's also a b involved. This is a kind of unfolding parameter. I put the a back to 0. And now I'm going to let b increase. What I'm going to do? b, x, y, z. It should work now. Oh, why I'm making mistakes? Oh, perhaps this is the case. Yes, that was the problem. The size. Okay, now here you have the point almost, and then here you get bigger and bigger. And what I want you to show is that you have a triple point here in the middle, and you have a set of Whitney umbrellas just over here. Perhaps in some other color this is nicer or not. No, not such nice colors. Just what you like. And to see that there is also an inside, then you can just move the sphere, and then you see what you don't see now. Okay. Oh, I put the a again equal to 0. And then I have this guy. And now I want to get a little bit in the inside. And here you see the triple point. So, okay, so this is the way you can play with this, and perhaps we come back in certain examples. Okay, so let's keep the picture there. It will get out after some time. And I will do certain things now on the blackboard. Okay, completely unrelated to these pictures up to now. Okay, I really want to go back to the most elementary beginning. What was the Milnor vibration? And to compute that in certain examples. So we had F to C. And we then have always this picture. This is a sphere. This is the singular point. This is a disk, and you have a neighborhood. And somewhere in here you have this special point, typical point, and you have the smooth nearby fiber. So you can put this on the boundary if you want. And then we showed that if you have an isolated singularity, that this Milnor fiber was very nice. It had a bouquet of spheres in the middle homology. And the other ingredient which people, so the Milnor fiber is F, and the other ingredient that people look at is the monodromy. Since if you have a vector field here, you can lift it everywhere, and you can walk around and come back. And in fact, you come back almost always upside down. There are only very few cases where this monodromy is the identity. And in the isolated singularity case, it's only the case that there are no singularities. But I promise not to tell new things. Let's first try to look again, and Lorenzi also did already, to look at the case of two variables. Then locally, the Milnor fiber is given by fxy is equal to t. And so what are the dimensions? So then I have a map from C2 to C. So the fiber is one complex dimensional. Okay, what could it be? Okay, if things were smooth, and the Milnor fiber is smooth, and if it's complete, so to say, has no boundary elements, we know we have Riemann surfaces. So it is a part, F is a part of a Riemann surface, part of Riemann surface. An oriented two-dimensional surface. And let's take some examples. So one example we are going to look at is x squared plus y cubed. What do I have more? X squared plus y to the power 5. And x cubed plus y cubed. Okay, but then the important thing is that where we cut the boundary, then you see a point here. But what happens is you have a two-dimensional real surface cutting a three-sphere. So you get circles. So you get, could it be this? So this has two boundary components, since it has two irreducible components, x plus I times y and x minus I times y. So it are just two planes. Is there a hole in the middle? Here, this is an irreducible guy. So this has only one boundary component. So this is something like this. Question, is there a hole? And how many? Same question for this guy. And here, so homogeneous degree 3, 3 linear vectors. So we have 3 boundary components, kind of pans. And is there anything in the middle? Okay, we are going to compute that. The Euler characteristic of a Riemann surface with G holes is 2 times 2G. How do I remember this formula? I know this formula not so precise. So now I test G is 0, no handles. And the answer is 2, it's a 2-sphere, and G is 1. A torus with 1 handle, and the Euler characteristic is 0. So it's the right formula. Okay, so this is, and what happens if I have a number of holes? Then the Euler characteristic of my Milnor fiber is 2 minus 2G minus the number of holes. And R is the number of irreducible components. And the other way, we know that these things are bouquet of spheres. And we also know how many spheres. We can write down the Milnor number. Mu is 1, 2, 4, and 4. Okay, so this is equal to 1, since this is connected, the B0 minus the Milnor number. This is correct. So 2G is equal to 1 plus mu minus R. Okay, we can test that in these examples. Mu is 1 over here. So this is 2G is equal to mu is 1, the 2 minus G is 0. No hole. So then we take the next one. R is 1 in this case. Oh, perhaps I did the wrong thing, but is it the right formula? I hope so. R is 1, this is 2, mu is 2, this is 4, G is 2. Is G 2 in this case? I have the feeling I made a kind of calculus mistake. Is this okay, this formula? Yes, okay. So let's try to do this guy again, since I know G has to be 1 in this case. And so mu is 2, so I have 3 minus 1 is 2, so G is equal to 1. Okay. And if you do it, then you get here G is equal to 2. And let's also try this one. Has Milnor number 4. So this is 5 minus 3 components. 5 minus 3 is 2, so G is also equal to 1. Okay, now you have, I hope, a good idea that what such a Milnor fiber is in this. And then you can the complicated process of taking, say, in one of those examples, your Milnor fiber here and turn it around and let it come back. Then you know that there are generators of the homology, and they have as image combinations of the generator of those generators. So there's a matrix involved. And the difficulty is, in general, to find out exactly how that matrix is. It's not so easy. But I will treat some easy examples with you, since the other examples are too difficult. And this is more or less what we have been doing before. We take first a one-dimensional case. So this is a map from C to C. Okay, then I know that the Milnor fiber consists of 4 points. In fact, it consists of 1. It consists of the 4th roots of unity, the 4th roots of unity squared, and the 4th roots of unity to the power 3. 1i minus 1 and minus I, but I write this, since if I take x to the power 5 equal to 1, I get something similar. And if I call this E0, E1, E2, and E3, then the generators should have to take the relative homology to the case that you have only 1 point. The singularity has itself, the solution for x is, the singular solution is x is 0, is 1 point. So you have to take the difference. F1 is E1 minus E0, F2 is E2 minus E0, and F3 is E3 minus E0. So these are generators. And in this case, it's easy to find how the monodromy works. The monodromy is multiply by psi4. So, and then you move all the points from one to the other, and you stay in the Milnor fiber. So that means if you take your monodromy, you get A2 minus A1, which is F2 minus F1. You get A3 minus A2 is F3 minus F1, and you get A0 minus A1, which is minus F1. So the following matrix, minus 1, minus 1, minus 1, 1, 0, 0, 0, 1, 0. Okay, it's not diagonal, it's just the matrix. And then you have to do your calculus, you compute the characteristic polynomial. You put minus lambda in the diagonal, so that we teach in the calculus, in the linear algebra course. And then or you take your computer and you have the answer, or you use 1 or 2 minutes to get the answer, and the answer is lambda to the power 3 plus lambda squared plus lambda plus 1. So perhaps you have seen this already, it's in your lecture. And so the roots, so the eigenvalues, are as follows: 1/4, 2/4, and 3/4 as exponent of 2 pi I bracket. So 3 eigenvalues, and one is not the eigenvalue, the 0, which is the eigenvalue 1, is not there. Okay, so one thing to remember, that in this curve case, the trace always has to be minus 1. Oh, if you do this for x to the p powers 1, so x to the p is 1, you get a set of eigenvalues 1 over p, 2 over p, until p minus 1 over p. Okay, so this is a function of one variable, and we have done them all, anyhow, all isolated singularities. And then we are going to take special cases. Isol 2, Isol 1, Isol 2. This was Isol 2. Please check the, I don't need input at the moment. So then we have this kind of joint principle. Okay. So if I have the Milnor fiber of x squared plus y squared, I remember the construction of that we have seen. Then we have 3 solutions in one case and 2 solutions in the other case. And then you match them. And then you see, easier than in the lower dimensional case, that there are 3 cycles. And Milnor number is still 3 in this case. If you take x to the power 4 plus y to the power 3, you get more or less the same picture, but then you have to add an extra point, a third point. And let's say you take this point. And then you get just the double amount of cycles. So mu is equal to 6. And then the idea is that if you take monodromy, that this is a kind of machine. So we know that for the monodromy, we have to turn around these things for the x coordinate, and we can turn around the other 2 for the other coordinate. And what we just have to do in these cases is to take the eigenvalues, which are in this case 1/4, 2/4, 3/4, and 1/2. And then we have to make the combinations. So here we get 3/4, 1, and 1/4 out of it. So we get the same eigenvalues as before, but with a shift of a minus sign. If you do the other way around, this one, 2/4 and 3/4, then you have 1/3 and you have 2/3. And then you have to make your 6 combinations. So they will have denominator 12. And so if it so this is 3 plus 4 is 7 divided by 12. That is 6 plus 4 is 10. Oh, you have to add 3 at the time. 10. And I have 13 over 12. And for this guy, I have to add 3, I think. So this is 3 plus 8 is 11. And now I have to add again 3, I think. 13. Okay, so we make your homework. And so it's easy to get the eigenvalues here. And because 3 and 4, you cannot divide them, you will never get eigenvalue 1 here. The same thing works if you put another coordinate to some power. These are for the moment I wanted to, or everything I wanted to say for the monodromy in the isolated singularity case. Other questions? I did not understand you. Okay, you say it a little bit louder, since others come here and write down what you want to say.
So when you compute the monodromy with this Thom-Sebastiani thing, right?
Yeah.
You don't use an eigenvalue of 1, no?
I don't found here eigenvalue 1. Yes.
Yeah, but can you say something about why not using that?
Because if you take the combination of these numbers, you can never get an integer number. If in the range you see here, if you make those sums, where you always find a lot of eigenvalues, the dangerous case is if you x to the power d plus y to the power d. Then you have in both cases combinations of d roots of unity. And then there are always combinations, lots of combinations. So you have to add k over d combine it with L over d. And then you can make lots of combinations with eigenvalues 1. So if you take this example, then you know that the eigenvalues, they are fourth roots of unity. And so you find 2 times eigenvalue 1 and 1 over 4 plus, people just write it also in this way. And they say this is the spectrum in a certain sense of the singularity. Okay, so the homogeneous case is the, so to say, the dangerous case for eigenvalue 1. Oh, in the beginning.
Yeah,
Yeah, that was the computation.
Yes, yes, that was the question.
Yes, and in
so that's
fact
why-
there is an eigenvalue 1, but that is not on the level of this H1, but on the level of H0. Since then, the H0 measures the number of connected components, and there's only one connected component, and it goes as the identity. And that there's a kind of statement that the alternating trace is always 0. Okay, so now we go to non-isolated singularities. Anyhow, this is much nicer than PowerPoint. And it goes also a little bit slower. Okay, so what do we remember from the non-isolated singularity case? Okay, in the case of the singular locus dimension 1, there were some formulas for the dimension of h(n-1) of f, which was the, in this case, no, this is general, which was the sum of the co-kernels of, no, this is not. There was a group defined as delta 2f, which was the so-called second boundary. And I will show, and that was the sum of the co-kernels. And there was also the Hn of delta 2f, which is the sum of the kernels of AI minus identity. And this means that and there was a surjection to the Hn-1 of the Milnor fiber. The surjection, and that means that the dimension of the Hn-1 of f, as that is called the Betti number by my teachers, is equal to the sum of the dimension of this kernels or co-kernels. It is smaller and equal than that. And the last one is equal anyhow than the sum of the so-called transversal Milnor numbers, where I is numbering the number of components. So you have this kind of picture. You have a singular set, which can have several components. And then we could take a transversal plane over here, and we could walk around over the singular set, since the singular set is real two-dimensional, so it also cuts the boundary in a circle. And you have here this singularity. So in the picture, you could have a singularity here. And it's Milnor fiber over there. And this transversal Milnor fiber goes goes into itself by a monodromy. This is not the Milnor monodromy, which I computed. It's the vertical monodromy or local system monodromy. Okay, and we have already seen several examples of this. Okay, the examples, they were D infinity, which is the Whitney umbrella xy squared plus c squared. which appeared just an hour ago. And we have also seen the triple point okay, so okay, this equation x, y, z is equal to 0. And here you have just the ingredients of this vertical monodromy. And we have already seen that for d infinity, there is a single vertical monodromy, and this is minus the identity. Just an hour ago, we also computed the Milnor monodromy, which is, I think, also minus the identity. Then we have here 3 singular components. Or should be made in red or orange, but and then on each of those components you have these vertical monodromies. And how do you generate the vertical monodromy? By writing x, changing x in e to the macht 2 pi I s times the original x. So you walk around in the plane y is equal to z is 0. And then this you try to follow by y and z. And then you take z as constant. And you take for y the opposite. And then this product is all the time the same as before. And if you want to walk in the Milnor fiber, you also stay in the Milnor in the same fiber. And this shows that this vertical monodromy are all equal to 1. And you can also compute Milnor monodromies, and in this case they're also 1. So this is, if you want to compute the Milnor monodromy, then you have to do the same type of trick. But you have, you can use all those 3 things, and you can take the same map, so to say, and you stay in the fiber. Okay, this is good to remember. Oh yeah, the Milnor fiber. We did not compute the Milnor fiber. And it's very good to do that, since x, y, z is equal to 1. Since it's homogeneous, it's not necessary to take a small t, since you can always multiply from the origin and get this. Okay, how to get the Milnor fiber here? Okay, what you can do is to take polar coordinates. X is R1 E times 2 pi I alpha 1. Y is idem is 2. And the same thing with R2 and R3. And then you take the absolute value. And if you take the absolute value, the equations R1, R2, R3 is equal to 1. That is the equation for the absolute value. But they have to be positive. So what you get is a kind of piece where you see it's a contractible piece. It's a kind of piece of, it is not a hyperbola, but it's just something contractible. If you look to the arguments, you get that alpha 1 plus alpha 2 plus alpha 3 has to be 0 mod 2 pi. Okay, you draw in your argument space, which is a cube, since you have to identify the 3 torus. You draw this guy. Yes, but it also continues here. And then you do some cutting and pasting. After cutting and pasting, the answer is the 2 torus. 2 torus. So this is the first Milnor fiber I described, which is not a bouquet of spheres. So they also exist not being a bouquet of spheres. Okay, so this was treated this already. Okay, no, let's not make it too late. Okay, then we go to the Zariski example. With 3 cups. And degree 4. Which is start almost the same as what I showed before. The beginning is the same, plus minus 2 x, y, z, x plus y plus z equal 0 in C3, but algebraic geometers, they look always in P2. And since then you can make this kind of pictures. But I just look in C3, so it's the cone over this. So where you have 3 singular lines, and each with transversal type a cusp. Okay. But using this kind of formulas for h1 of f, n minus 1 of f, and for this guy, we have just to use this transversal monodromy. So here you have a cusp. Okay, so what did I want? I want to compute AI. But I did not compute it AI. I know how to compute TI, the Milnor monodromy. But there is Steenbrink's idea, Joseph Steenbrink, and he showed that F is homogeneous of degree D, then AI is Ti to the power minus D. So in that case, you can compute from the Milnor monodromy, since we have just computed that, this AI monodromy. So this is only works in these cases. This formula is easy, but some people, they don't remember, or they don't read the literature and find these type of formulas again by themselves. Okay, it's already 30 years old, the formula, so have also been, lots of us have also been forgotten what the Italian geometers had done 100 years ago. Okay, so what was this? This was the cusp, x squared plus y cubed, and we had already computed, I think, let's do it again. So this is 1/2, and to combine this with 1/3, and 1/2 to combine this with 2/3. So this is 1/6, I think. And I have no. Yeah, the answer is okay, I think. But I have to do plus. So this is 5/6. And the other is 3 plus 4 is 7/6. This is indeed the same as 1/6 and 5/6. Okay, so AI is Ti, so this is Ti to the power -4. Okay, then if I have to take this to the power 4, so I get as eigenvalues 4/6. And of course, the other one will be 2/6. Okay, what do we see if you look here? This co-kernel, anyhow, the kernel is 0, and the co-kernel has dimension 0. So the conclusion is that that the dimension of Hn-1 of f is 0. And since we can also compute Euler characteristic, we know all the homology, the dimension of all homology groups. Okay, but this example also shows that the homology group itself has torsion. And let's try to look if I can get my my input signal. Please take the TX input signal. It's coming back. Yes, also my computer is coming back. But surging. Yes, it's there, but not there. But the answer is here. So this co-kernel is Z3. So this co-kernel is in this example C3. And how do you compute that? In most of the cases, because people, they could compute the in some completely other way. They could compute the fundamental group. And if you know the fundamental group, you can make the abelian version. And then from that point of view, you know that, that the answer is 0. Okay, I also made a picture of this. And just let's try to find, if I can find this in the even kijken, documents, de Z of Sariski. Documents, server. The documents, and then also look to have a server picture. Yeah, Sariski server, it's here. Okay, so this was the picture which I made in the break. And now you have to, anyhow, it's possible to see the cusps here. I don't see 3 cusps at the moment. Or do we see 3 cusps? Yes, perhaps we see them. Always difficult. Okay, so this was then a picture in server. So this was one of the example of homogeneous singularities. And then I have still one other example, and then it's time for the weekend. Okay, just the right organization now. So too many different sheets. Okay, there was so that I will not treat that. There is also this. The sextic curve with Sariski, with 6 cusps, and 2 cases, one on the conic and the other not on the conic. But it's again the cusp, but since the degree is 6, in that case you have Ti to the power 6, and that means that the 6 powers of these guys, they all become 1. So then the co-kernel and the kernel you have is more or less everything. So this is not helpful to get the answer down to what you want. Okay, then we have still one example to go. If anyhow to clean this. And I can also put something on the screen of that. Where is it? Is it here? Yes. Okay, I'm going to take the thing in this formula. So I start with x squared, y squared plus y squared, z squared plus z squared x squared is equal to 0. And then I do my computation, and I see that the singular set are the 3 coordinate axes. Sigma are the 3 coordinate axes. So if I go transversal on one of these axes, so let's take the x-axis. So you take x is a constant, c. Then you see this is y squared, z squared, and something which is above of higher degree. So y squared plus z squared is dominant. So this is an ordinary double point. So I just transversal, then I write this in this way, A1, transversal A1, transversal A1. Okay. Then there are also to compute the Milnor fiber, and we have to compute these monodromies. Now you can try to do that, but my advice was to take a deformation, which is also written there, and take the deformation minus S, X, Y, Z. And so this was the first thing I showed you after the introduction in the server program. You saw the point unfolding to a kind of bubble. Okay. So what happens if you do this? You found those bubbles here. Then on each of those axes, you get some points where the transversal type is no longer A1. It's so kind of special point. In the middle, you get this x, y, z is equal to 0. If you want, you can now use every plane over here. Every plane over here. So that this is c is 0, y is 0. Then we have these two special points and a triple point in them. And this vertical system monodromy can be computed by walking around each of them separately and taking the composition. What do we know? The transversal Milnor fiber has homology Z, it's a sphere. Here the transversal monodromy is multiplication with -1. Here is multiplication with +1. And here is multiplication with -1. So altogether, also here the transversal monodromy Ti on each of those things is equal to the identity. Yeah. Who do I know the deformation? Because I invented it. No, but the idea is, of course, you see, after having the example itself without the deformation, you see that they have three, you see the singular set, which consists of three coordinate axes. And then you say, okay, if I want to deform it in such a way that on the Milnor sphere, I have still the same three axes there, but in the interior, certain things are allowed to change. And what you can do in this case is to take the easiest example with this singular set and put this in a family. And then you get, so to say, the first family above. Having done that, you can just go and look and count the number of points. Okay, what I see is the 6 d-infinity points, the Whitney umbrellas. See that in the picture and on the screen. Then there was one triple point, but I claim that there are 4 A1 points. 4 A1 points, you don't see them since they are not on the zero surface, but they are singularities of the function. So if you look to the original picture with the bubbles of this, I think I also have this picture here completely in the beginning. So this is a nice thing of having your own computer and not the system. Okay, then here you see this, you have 8 different pieces in space. In 4 of them you have a bubble. And inside the bubble you have a critical point of your function. So these are the A1 points. Now, then I have to go back. And just so that I can do it faster now. It's going here, back here. Yes, yes, it's here. Okay, and then there is a kind of formula with counting Euler characteristics, and this tells you the Euler characteristic. And now there is some other point. So my statement is that you get a bouquet of spheres. And what I explained in the lecture was, as soon as on each component of the singular set, you get a d-infinity point. A d-infinity point is a singularity which has killed the first homology. Since in the neighborhood you have these transversal things which have first monodromy, but this guy is a two-dimensional sphere, so the first homology group is killed there. And there is a very nice killing principle. As soon as you can kill on one place on each component of the singular set this homology, you have killed it for the Milnor fiber. So you know now, even on the homotopy levels, that you have a bouquet of spheres. And then you can count the number of, there's a kind of Euler characteristic formula, and there are 15 spheres. Coming back to your question, how do you know this deformation? The deformation that I did not know is the second deformation. Look. So what is happening? If you have the 3 coordinate axes as an algebraic curve, you are allowed to, you can deform it as a curve to a smooth curve with some genus. And what I did was doing that process. So I changed here the formula a little bit, which is A1 and A2 and A3, which is just the deformation of the curve. And now in the deformed curve, I have something smooth. And then I can again play that game. And the game is then counting, finding out how many special points there are. And now I have this, now I have no triple point, but my curve has a kind of, has some homology. So I apply again the formula for the Euler characteristic, which is just counting and multiplying. And since there are d infinity points and there is one component, also this shows that the homology is killed. And I have a bouquet of spheres. And of course, then you ask why you cannot do the same thing with x, y, z. So you can deform the singular set, but within x, y, z, you cannot deform it. You can deform the three axes, but you cannot follow this by your function. So to say, the function has to be in the kind of integral of the Jacobian ideal. So that its derivatives are in the Jacobian ideal, and this is is not the case for x, y, z. And so this should be a good task for Terry to have this kind of problem. So at a certain moment, quite often it turns out that if you are doing something with a given critical set, that the first few things you are looking, the elementary building block, is kind of Richardsing, and has not a bouquet of spheres. But if you go a little bit up, if you find a slightly more difficult thing with the same critical set, then it can turn out to be still a bouquet of spheres. But I think I'm going very over time. So I want to close and, of course, answer questions, but that can also afterwards. Thank you. Okay. End of the day.